Hi, I'm Prof. Joe, and this is part of my lecture on measurement technology, today talking about sensor technology. Since sensor technology is a very broad field, I'll just pick out some important sensor types, go into some details about them, and I will be not able to cope any sensor topic out there because it's as I said, it's a broad field. So let's start with magnetic fields, measuring magnetic fields. Why is that important? Because it's an important part of measuring currents. And measuring currents indeed is important for industries out there for several reasons, as you already know, I think. So, what to say about magnetic fields? First thing, talking about magnetic fields as a physicist, those magnetic fields are coupled to electric fields. So when there's a magnetic field, normally there's an electric field. And the coupling between both is via the induction laws. So the most important stuff for us is that whenever a magnetic field changes in any which way, we will get an induced voltage, which is minus d phi over dt, whereas d phi is nothing else than somewhat the magnetic field multiplied by the area it covers. So you see what we need? We need some change in the magnetic field or in the area the magnetic field changes. So moving a coil into or out of a magnetic field would induce a voltage. And that is something we can measure. And that would be a way, indeed, to measure the magnetic field a current would exert when flowing through a wire, actually. That's an important part for the obvious reasons, to get to know that whenever magnetic field changes, we have voltages. And another important fact is about the classification of magnetic fields, meaning there are different materials out there, you know, there are magnets, and so magnetic fields are classified by that permeability you see here, which is the product of two permeabilities. So we have the magnetic field constant over here, and we have the relative permeability over here, and that permeability changes in respect to the material. So there are, for example, there are diamagnetic materials, which repel the magnetic field from their inside. Means stuff like water or nitrogen just expels the magnetic fields from the inside. Then there are paramagnetic materials. Those have some permeability smaller than 1. Those have a permeability larger than, at least larger than 1. Examples were oxygen or air, which have some atomic magnets which can align to the external magnetic field. So when that permeability further rises to larger values, we get to the ferromagnetic materials, and as the name already says, examples would be iron. And though we have a lot of atomic magnets in iron, which can be aligned to the external magnetic field. By that, leading to another phenomenon, which you perhaps know, which tells us that the magnetic field somehow depends on the external magnetic field. So the magnetic field of a material, the overall magnetic field including the material, somehow depends in a certain way on the external magnetic field, and that certain way comprises a hysteresis, meaning that, I try to paint it properly, meaning whenever we start to magnetize, so increasing the external magnetic field, those atomic magnets in the materials will align, and then at the point we are decreasing the external magnetic field again, those aligned atomic magnets will still keep aligned. By that, changing the overall magnetic field for the way back, for the way when we decrease the external magnetic field, showing a rest magnetization when there's no external magnetic field over here. That's at that point over here. So that's what we all know happens when we use a magnet and couple it to iron. That iron will keep magnetized somehow a little bit until we smash it or hammer on it or something like that. And that happens all the way down. We change the magnetic field into the other direction and all the way back. And that means for changing magnetic fields, we have to think about that hysteresis, actually. And now, finally, how to measure magnetic fields. One way would be the use of induction. That's okay. There are measurement instruments out there using induction for measuring magnetic fields. We have a problem. We have to deal with that time dependency. So we have to integrate. And that makes that measurement method somehow complicated. Let's describe it that way. The most often used magnetic sensors are Hall effect sensors, which are nothing more than something like a block which can conduct current. And now we send a current through it. And by that, all the electrons over here can interact with the magnetic fields according to the Lorentz force. So that Lorentz force is defined as minus Q times cross product of speed and a magnetic field. And so those electrons have a speed in the direction of the current for sure, and they are, for that sketch, they are perpendicular to the magnetic field, and by that we get a Lorentz force which then indeed will deflect the electrons a little bit to the side. We won't go into the technical details about the physics, but what we see is that more electrons will be deflected to one side than electrons will stay on the other side of the plate we have chosen here. And that means, indeed, we can measure a Hall voltage over here, which is indeed very directly correlated to the current which flows through our Hall sensor and the external magnetic field. Kb just comprises a material constant which includes the size of the conducting material, the material itself, and which is described by the Hall constant and some more material parameters. We won't go into details about that. There's an easy derivation of how that formula exerts. You can use the AI-Tutor, which is linked below, to get more details about the derivation of that fact. But for now, it's enough that we know there are Hall plates out there, Hall sensors out there, which give us a voltage which is directly proportional to the magnetic field. And that's quite usable. We have some more facts about those Hall sensors, like the one shown here. We can get hold of the direction of the magnetic field. As you see, the direction of the plate is important for how the magnetic field works on the current flowing. So when we somehow get an angle to the magnetic field, the electrons are not able to be deflected as much as when we are perpendicular to the magnetic field. So we can get hold of the direction of the magnetic field. Moreover, using such a Hall sensor, we have to think about some other facts. One is that still induction works. So when we have a changing magnetic field, a time-dependent magnetic field, we will induce some additional voltages to the Hall voltage itself. So there are some zero conductance components to the Hall sensor we have to think of when measuring a magnetic field which is time dependent, which changes with time. In the next part, we will talk about some current sensors. Some current sensors using measurement of magnetic fields and some current sensors not using magnetic fields. See you then. Have fun.